Hello students, this is our lecture number 57 and today we will complete this chapter also. We will discuss some numericals on shear stresses on the beams and we will also draw the shear stress distribution diagram. How the shear stress can be calculated at different layers. We will check it right now. We will solve two examples today. First for the T section and second for the I sections. In the T section as well as in the I section, we will calculate the layers. We will calculate the shear stresses at different layers of the section. Let us see how. First example for the distribution of shearing stress over a T section. You can see what is the data given in the example number 6. T-shaped cross section of a beam shown in figure is subjected to vertical shear force of 100 kN. You see, vertical shear force is 100 kN, means capital F, which we will use in the equation. So F equal to 100 kN. Calculate the shear stress at important points. Important points means what? You can see in this section, in the figure, the top layer, the bottom layer, means bottom layer of the flange, and at the bottom layer of the web. These three layers are subjected to shear stress. We will calculate it later on. We know that in the theory, according to the theory, at the top layer and the bottom layer of the section, the shear stress will be 0. So at the top layer, at this layer, and at this layer, at the bottom layer, at these two layers, the shear stress will be 0 as per our equation. So we just have to calculate three values of shear stress. Remember, which three values? You just see which three values we have to find at which point. You can see, first of all, we will calculate the shear stress at this corner, means at the bottom of the wave and as well as at the outer corner. Then after we will calculate the shear stress at this corners, means at the corner of junction of wave and flange. And third one is the center of gravity. Some center of gravity will be somewhere over here for the entire T section, and at this layer we will find the shear stress. So we will find three shear stresses. This is first, this is second, and this is third. And out of these three values, one value will be maximum. The maximum value will be at the center of gravity, as we know, or it may be at the layer 1 or 0.1 or 0.2. You can see in the figure. We don't know where the shear stress will be maximum. So we just want to calculate these values, and then after drawing the diagram, we will check which shear stress is having the maximum value. Let us see how. What is given in the data? It is given that shear force F is equal to 100 kN. So 100 into 10 raised to 3 in newtons. Moment of inertia is 113.4 into 10 raised to 6 mm raised to 4. Actually, moment of inertia we have to calculate as per the previous method. So you just know the previous method to find the moment of inertia about horizontal central axis for this T section. Before that you have to find center of gravity also. So just start center of gravity y bar. So what is the formula of y bar? A1y1 plus A2y2 upon A1 plus A2. Okay, so this is A1, means area of the top flange, which is 200 into 50. Into y1 means the distance of center of gravity of the first part, means wave from the bottom of the T section. So this is the bottom of the T section. Starting from this is the 200 and midpoint of this will be 25. So 225 is the distance. So this is A1 y1 plus A2 y2 means second area and the distance, means 200 is the second area, 200 into 50, and the distance of center of gravity will be at the midpoint. From the bottom it is 100. So it is 100. Now divided by A1 plus A2 means this two brackets itself. So answer of y bar will be 162.5 mm. So this is the regular method to find the center of gravity, and then after you can calculate the moment of inertia about horizontal central axis IXX, which will give the value of 113.4 into 10 raised to 6 as described. Let us see how the shear stress comes into the picture. This is the distance YC. YC means what? The upper layer distance from the center of gravity. So it is 250 minus y bar itself. Y bar somewhere over here, which is 162.5 from the bottom. But the total depth is 250. So 250 minus y bar will give you YC, means distance from the center of gravity to the upper layer of the T section. Now Suppose we know that area of the upper flange. Now we are starting the calculation of shear stress and we want to find the shear stress at this layer. And at this layer also we want to find the shear stress at 2 points, at the outer point and at the corner point. So let us see how. So for this you just remember the method. This method is very complicated. So concentrate accordingly and concentrate very peacefully. First of all, area of the flange, upper flange. Why I have taken the area of the upper flange only? So if you are finding the shear stress at this layer only, then you have to take area of upper portion or upper section of the layer only. Okay, again repeating. We want to find the shear stress at this layer. So area must be taken above this layer. Above this layer only one rectangle is there. So take the area of that rectangle. So which is 200 into 50, which is 10,000 mm square. Now what is Y bar? First one is area, which is completed. Second one is Y bar. What is Y bar? So Y bar is the area which we have taken. Center of gravity of that area means at this point, you can see in the figure, at this point is the center of gravity of marked area, hashed area. From this center of gravity to the main center of gravity of the T section means this distance, again repeat, this distance, again repeating, this distance is known as Y bar. So how we can calculate that? This is 162.5, which is already a Y bar as we have calculated 162.5. So just before finding that, 200 minus 162.5, which will give you the answer of 38 point something, plus this 25. This is 25, which will give you the answer of 62.55 mm. Remember this, 87.5 minus 25 by 2. You can see, you can start from the upward also, from YC also, from bottom also. At anyhow, you have to find this distance, this center of gravity and main center of gravity of the T section. So in between these 2 points, this distance is known as Y bar. Okay, hope you are getting this very clearly. This is very complicated. Just repeat my words from the video and just calculate the Y bar. Now what is B? B is equal to 200 mm. How the B will be 200? It is the width actually. Okay, it is the width actually. So you can see width of the wave or width of the top rectangle is 200. So here it is taken as 200. Now we have taken 200 means from this corner to this corner. You can just repeat the figure, this corner to this corner. So we will find the shear stress at the corners only. So now applying the formula of tau is equal to F A Y bar upon IB, which is equal to F means 100 into 10 raised to 3, area 10,000, Y bar 62.5, which Y bar? This Y bar, not the center of gravity itself. Center of gravity, that Y bar and this Y bar is different. In this formula we have to find this Y bar only, which we have calculated recently. Upon IB, I means 113.4 into 10 raised to 6, which is given in the data actually. That is also you have to find. The sum is very lengthy and B equal to 200. So this will give you the answer of 2.76 megapascal means Newton per mm square. So at this corner, the value of shear stress is 2.76 megapascal. Let us now find the shear stress at this corner, means inside corner. Let us see how the shear stress can be found out at inside corner. Let's check. This is the shear stress distribution diagram actually. At the inner corner, or you can see at the whatever corner, at this corner the value of shear stress is 2.76. At the top fiber the value of shear stress is 0. This is our y-axis. So looking from y-axis, the right side values are increasing, which denotes the shear stress. So these two values, first value and the second values, are completed. Now we want to calculate the value of inside corner, shear stress at inside corner, which will give you the answer of 11.04. Then after we will calculate the shear stress at this point. We will calculate the shear stress at the center of gravity, which will give you the highest answer 11.64. by the formula. So we have to calculate 11.04 and 11.64. These two values are remaining as it is. Rest of the distances are calculated earlier. Let us find the shear stresses at inside corner and at the center of gravity. This is the shear stress distribution diagram which you have to compulsory draw in your answer sheet. Now looking over this, you can find that the shear stress at the junction suddenly increases from, at the junction means at this corner, okay. At this corner, the width will be taken as inside width, which is 50, you can see over here. So you just have to put the tri ratio. How the tri ratio should be replaced over here? Like this. When the width is, you can see, remember or listen carefully my words. This distance is 200, means width is 200, then the shear stress is 2.76. Okay, again repeating, when the width is 200, then the shear stress is 2.76. Then, if the width becomes 50, then how much is the shear stress? Okay, this is the tri ratio. When the width is 200, shear stress is 2.76. When the width is 50, how much is the shear stress? So by replacing the tri ratio and cross multiplication, you will get the answer of 11.04 megapascal. Hope you are getting me. So 11.04 megapascal is the final answer of yours. Now at the center of gravity. So let us see the center of gravity calculation now. You can see we have to find the center of gravity shear stress, means at this point. So upper area means first rectangle as well as this small rectangle. These are the area above the center of gravity layer. So this area are taken as A, and M2 y bar will be multiplied. We will calculate the y bar for this bracket and we will calculate the area for this bracket. So this is the A and this is the y bar. Actually here it is the multiplication, not the plus sign. It is printing mistake. Here it is the multiplication. Now what is the area? First rectangle is 200 into 50, which is written in the bracket. Now what is the second area? 62.5, which you can find out from this values, 62.5. No. Sorry, it is actually my mistake. Again repeating, what is actually A1, Y1, A2, Y2? Here we have to find the AY bar. So in case of AY bar, here this is the center of gravity layer. So this is the part number 1. Okay, this is the part number 1, while this is the part number 2. So the first bracket will represent the value of AY bar for the part number 1, means A1, Y1. And this bracket will represent the value of AY bar for the part number 2, means smaller rectangle, which is denoted by A2, Y2. So what is A1? 200 into 50 means the area of top rectangle. And what is Y1 for that? Means Y bar for that. It is the distance of this center of gravity, means a center of gravity of the top rectangle, to the center of gravity of the original T section. This distance in between the CGs is known as y bar, which is 62.5, which you can calculate from the earlier images, or you can calculate from the CG also. Now for the second part, the area will be 50 is the width of this rectangle, and this height will become 37.5, means 200 minus this y bar. You can get 37.5 into 50 as an area. And the distance from this center of gravity to the main center of gravity of this smaller rectangle from the main center of gravity, in between this 2 CG, the distance is 37.5 by 2. So final calculation will give you the answer of 660.2 into 10 raised to 3 mm cube. So this is very awkward calculation. You have to practice for this. And the width at the inside corner, or width for the CG section, means at this section the width is 50. So B is taken as 50 in the formula. So this is the calculation. Now the formula is very easy. Just replace the value and you will get the answer. So tau max is equal to FA y bar upon IB. F is given in the data 100 into 10 raised to 3. A y bar is calculated earlier. I means given in the data and B means 50 is the width of the section. So final answer is 11.64 megapascal, means Newton per mm square. So at the center of gravity, 11.64 shear stress is acting, which is the highest maximum shear stress. So for the T section, the value of shear stress will be highest. You can see in the data now, this is the value at the outer corner, this corner. At the top fiber, the value of shear stress is 0. At the bottom fiber, the value of shear stress is 0. At the inside corner, this corner, the value of shear stress is 11.04. Means when the width is decreasing, the stress is increasing. It is inversely proportional. At the center of gravity layer, at this point, the value of shear stress is 11.64. So these are the shear stress distribution diagrams which you have to calculate and draw in the figure. So this is the numerical for the T section. Now let us calculate one more numerical, that is for the I section. You can see in this I section what is given. The dimensions are as usual. The compressive stress in the top flange is not to exceed 17.5 megapascal. So compressive stress sigma is given to you 70.5 Newton per mm square. Bending moment. How much bending moment the section can take? So first of all, as per the previous chapter, we have to find the bending moment M, resisting moment capital M. And the shearing force is 100 kilonewton, means F is given to you. Draw the shear stress distribution diagram over the depth of the section, means at the each and every point we have to find shear stress distribution diagram. This is I section, which is very lengthy, very lengthy as compared to T section. We have to find center of gravity, we have to find moment of inertia, we have to find moment of resistance, we have to draw shear stress distribution diagram, we have to find again and again A, Y bar and B, and then after we have to calculate different shear stresses. So this sum is very lengthy, so concentrate very carefully around these figures. Okay, first of all, the compressive stress is given to you 70.5 Newton per mm square. Shear force F is equal to 100 kilonewton, 100 into 10 raised to 3 Newton. Let us calculate the CG first. So what is the CG? Three parts are there: horizontal rectangle, vertical rectangle, horizontal rectangle. So A1Y1 plus A2Y2 plus A3Y3 upon A1 plus A2 plus A3. So what is A1? First rectangle, which gives the area of 250 into 50. From the bottom itself, the CG of this part, first part, is 25 plus 250 plus 50. So answer is 325, you can see in the equation. For the second rectangle, this vertical rectangle, the area will be 250 into 50, which is written in the bracket. Center of gravity for this part, from the midpoint to the bottom, which is half of 250 plus 50. So 125 plus 50 is 175 written over here. And the third part, smaller rectangle, is 50 into 150, which is written in the bracket. And the distance of this center of gravity from the bottom is 25. So here it is written as 25. Simplification will give you the answer of 198 mm. So from the bottom itself, the CG will be somewhere over here, 198. So this distance is 198. Remember, this distance is 198. So you can write down this figure in your rough page for the further calculations. What is 198? How the upper distance comes into the picture, how the lower distances are coming into the picture. Now YC is equal to 350, means total depth minus Y bar is equal to 152 mm. YC means from the center of gravity to the top layer. This layer is 152 mm. You can subtract the values, distances, and you will get the YC and the Y bar itself. Now, important thing is moment of inertia. There are three parts to calculate the moment of inertia. You just calculate the moment of inertia as per this formula. Ignore this bottom line in the given page, but you just remember this page only. For the first part, here it is Ig plus AH square. So what is Ig plus AH square? If you remember the method, our first part is rectangle, so Ig is BD cube by 12. So BD means 250 into 50 cube. Here it is BD cube by 12, okay. Area will be 250 into 50A. And what is H bar square? H bar means Y bar minus Y1 or Y1 minus Y bar. Y1 minus Y bar you can calculate from the CG. So what is Y1? It is the center of gravity of first part from the bottom, which is 325, okay. And Y bar we have calculated as 198. So here is the method. Ig plus AH square. Ig means BD cube by 12 plus area of the rectangular part. H means Y1 minus Y bar. So for the similar method, second part is BD cube by 12. So B is the 50 for the second part and D is 250. So 250 into 50 is the area. And BD cube is 50 into 250 cube by 12. Y2 is 198. Here it is Y bar. Because the answer is negative, so we have taken Y bar ahead and Y2 afterwards. So Y2 is 175. You can calculate from the CG portion. Similarly, for the third part, you can calculate for this rectangle. B is 150 and depth is 50. And here it is Y bar minus Y3. So final answer is 502 into 10 raised to 6 mm raised to 4. So hence we can calculate the moment of inertia. In the previous numerical, we have directly taken the moment of inertia, but in this numerical, we can find the moment of inertia by this method. So you can find the moment of inertia in the previous numerical also according to this method. Now, our first question is bending moment. So as per our formula, bending moment is sigma upon y into I. Okay, because our equation is like this. Sigma upon y is equal to m upon I according to flexure equation in the previous chapter. Okay, so from the previous chapter formula, make the subject as bending moment m. So m is equal to sigma upon y into y. Sigma is given in the data. Yc we have calculated earlier. You can rewind the video and check it. Moment of inertia, just we have calculated 502 into 10 raised to 6. So final answer is 57.8 into 10 raised to 6 Newton into mm. You can convert it into kilonewton into meter, which will give you the answer of like this 57.8 kilonewton into meter. Here our first answer is completed only. Means we have just reached the previous chapter only, flexure equation. Okay, now we are starting the calculation of shear stress. So our this chapter shear stresses in beams is just starting now for this numerical. So it is very lengthy. You just concentrate. This is the shear stress distribution diagram. You can see at the top layer the shear stress is 0. At the bottom layer the shear stress is 0. At this corner the shear stress will be 1.26. At inner corner the shear stress will be 6.3. At the center of gravity the shear stress will be 7.36. At the outer corner of the bottom flange the shear stress will be 1.72. At the inner corner of the bottom flange, the shear stress will be 5.16. So this much values we have to calculate. Imagine what type of the sum is that. So I am just taking one or two parts, then I am going forward very quickly. You have to calculate at your own. So let us start with the first part. Means suppose we want to calculate shear stress at this corner only. At this corner, outer corner. So what is area? If you want to find the shear stress at this corner, just draw a line at this layer like this and just calculate the area above that. Area above that means this rectangle 250 into 50. So which is the area A? 250 into 50. 12,500 mm square. Here it is mm square. Power is missing. Y bar. What is Y bar? Y bar is the CG of this part, means layer above CG of the part above the layer to the main CG. Main CG of the rectangle means from this point to this point. Now this distance you have to calculate at your own. This is suspense. So y bar is equal to 152 means yc minus the upper distance is 50 by 2 means 25. So answer is 127 mm. You can calculate very easily. Nothing difficult. This width is b equal to 250 as you can see. Now from these three values and moment of inertia is already calculated, shear force F is given in the data. You just see what is the formula for tau. It is the tau is equal to Fy bar upon Ib. F is equal to 100 into 10 raised to 3. Area is 12,500. Moment of Y bar is given to you 127. Moment of inertia 50 into 10 raised to 6 and B equal to 250. You can check all the values which are calculated in the previous pages. So 1.26 Newton per mm square is the shear stress. Okay. Now if you find the shear stress at this inner corner, then the width will be 50 only. So again repeating the tri ratio, when the width is 250, the shear stress is 1.26. Then if the width becomes 50 only, then how much is the shear stress? So it is 1.26 into 250 by 50, which will give you the answer of 6.3 megapascal, which will be the shear stress at inner corner. So at the outer corner value is less, at the inner corner value is high. Okay. Now similarly you can find the center of gravity shear stress, this value, this value. So if you find the center of gravity shear stress, means at this layer you want to find the shear stress, then you have to mark the areas above that. So this will give you A1Y1 and A2Y2. Okay, so this is the corresponding areas 150 into 50 and all the values are clear with this method. So I am just repeating this numerical. You can see A is equal to 150 into 50 for this rectangle. Y bar will be 198 minus 50 by 2 means from this layer to the CG of this layer. Okay, below the CG. This is the distance. okay, which is 198 means y bar minus 50 by 2 means this distance, which is subtracted, so answer is 173, and the width is 150 only. So which will give you the shear stress at this outer corner. So just replace the value in the formulas itself as per our calculated values. You will get the shear stress as 1.72 Newton per mm square. And if you want to find the shear stress at inside corner, then the width becomes 50. So by tri ratio, you will get this value, 5.16. And finally, at the center of gravity above the neutral axis, A y bar will be above the neutral axis. A y bar will be, this is the first part and this is the second part, A1y1 and A2y2. So this is A1y1. You just calculate it at your own. This is A2y2. This is also you have to calculate at your own. You will get the answer of A y bar. This is suspense and this is for your practice, so I will not explain this. By our regular method, width will be 50 at this point. So replacing all the values, width is equal to 50. Replacing all the values, you will get tau max is equal to Fa y bar upon Ib. So again at the center of gravity, tau is the maximum. So you just calculate all this value and you will find the answer of 7.36 megapascal. So this is very complicated numericals. You just practice this two sections, T section and I section, and find the shear stresses at different points and draw the shear stress distribution diagram. So that's it for the chapter. In the GTU exam, only these two diagrams will be asked, T section and I section, and you have to calculate the shear stresses for these two sections only, nothing else. This is the conclusion of the chapter. So right now we are completing this chapter. In the next lecture we will start with the new chapter, fresh chapter only. Thank you students. Just remember this video. Just remember these two numericals which are very difficult. Practice at your own. Thank you very much. Ask for any doubts. Till then, goodbye.